Hello everyone, welcome to the session Impact of Free Jets. In the previous session, we seen the force exerted by the jet on a stationary plates, right? And moreover, we seen all these cases like when the flat plate is held normal to the jet, when the flat plate is held inclined to the jet, when the flat plate is curved. And in the curved, we have three cases, which is like strike the curved plate at the center, just strike the curved plate at point and tangentially, which is like a symmetrical one, and the third case is unsymmetrical one, right? And now uh, in this session we'll see the force exerted by the jet on the moving plate, right? And in these again we have the similar cases, which is like a previous one, which is like when the flat plate is held normal to the jet, when the plate is held inclined to the jet, when the plate is curved. Again in this curved we have two cases, and in each case we have a similar case, which is like a single vein and a series of veins, right? And now in the case one, jet strikes the curved plate at the center, and in the second one the jet strikes the curved plate at one end tangentially, and that too it is unsymmetrical one. And we know what is one end tangentially, which is nothing but at the tip of your blade, right? In these again we have the single vein and the series of curved veins, right? Once again, in the previous session we've gone through stationary plates. In this session we are going with moving plates. Okay, now the first case in the moving plates, the plate is held normal to the jet, and now here you can see the jet with the velocity v, and here the plate which is held normal to the jet. And now when the plate is here, the velocity of the jet is v. Okay, we can see here v. After striking the plate, it will move forward with the velocity of u, right? Here the velocity of the plate is u. Clear? And now after moving some distance, which is like u, here the jet velocity will be v minus u. Jet velocity will be v minus u. After that, the plate will move from here to here. Clear? And now the velocity, which is like v minus u, is a relative velocity. We call it as relative velocity, with which the jet strikes the plate is v minus u. And mass of water striking the flat plate per second, which is like rho a v. In the previous cases here we took v, right? But now you're taking like v minus u, which is a relative velocity, right? And according to the impulse moment principle, we have the force which is exerted in the x direction is equals to mass per second, which is like rho a v minus u, into initial velocity minus final velocity. The initial velocity is v minus u in the x direction, that is this one, and the final velocity will be 0, that is the velocity after striking the plate in the x direction is 0. And final equation is the force in x direction is equals to rho a v minus u whole square. And now this is very important. Like in the previous, when the plate is stationary, the work done is 0. We didn't discuss anything about the work done. Why? Because when the plate is not moving, the work done is 0. But here the work done, we have the work done. Why? Because the plate is moving from one place to another place. And now here the force into distance is your work done. And what is the force? And this is the force which is exerted in x direction, that is rho a v minus u whole square into u. And the next one, we'll see the next case, which is like the plate or blade is held inclined to the jet. Okay, this is the velocity v with which the jet is striking the plate, which is inclined with respect to the angle theta. And now this is your normal force. We know in the previous session we already seen these for the stationary plate, the normal force. and it will move with the velocity like v minus u, which is a relative velocity. Here you can see relative velocity. And now the force which is normal to the plate is mass per second. From the impulse moment equation, the force normal force is equals to mass per second into initial velocity minus final velocity. The initial velocity will be when it is making like theta, okay, and this is your initial velocity, which is like v minus u sine theta, and the final velocity, which is like 0. Here the final velocity is 0. And now after simplifying, the normal velocity, what your normal force, what you're going to get is OA v minus u whole square sine theta. And now actually what we require is the force in x direction, okay, force in x direction, which is Fn sine theta. If you see here you have Fn. If you resolve into two components, what you're going to get is Fx in the horizontal case and the Fy in the vertical case. And now Fn, here the Fn is there, and now Fx is equals to Fn sine theta, that equals to rho a v minus u square sine square theta, which is multiplication of this sine theta, and that equals to your Fx. And now the work done is the force in the x direction into velocity, and this is your work done when the plate is inclined to the jet. And the next one, this is your third case, the curved plate, the jet at the center. That means for the curved plate, when the jet strikes at the center, this is the case. And now here again we have two cases, which is like a single vane and the series of vanes. We are discussing here like single vane. And now we can see the jet velocity is v here, and this is your curved vane which is striking at the center, and after striking it moves with a relative velocity which is like v minus u, and this u is the velocity of the blade. Clear? And from after striking the plate, the velocity of the jet will be v minus u, which is tangential to the curved plate, and this is your velocity in the x direction, which is the reverse of your initial velocity, and this is the velocity in the y direction. And you can see here, and this is like theta and theta, like we can say by seeing this we can say that it is like symmetrical way. All right, and now we'll see the force exerted by the jet on the vane, which is like mass per second, which is rho a v minus u. You can observe here in the previous cases it is like v, but here it is, we have to take the relative velocity, which is v minus u, and the velocity in the x direction initially, and the velocity in the final velocity of outlet, which is like v to x. And finally if you simplify this, you will get the force in x direction is equals to rho a v minus u whole square 1 plus cos theta. Clear? See how you got this, why you got this cos theta. Here the velocity after swinging the plate is v minus u. From here you got this, which is in the reverse direction, v minus u cos theta, so that's why you got negative. And if you simplify this, you will get 1 plus cos theta. Similarly, you can also find the force for the y direction, which is like rho a v minus u square sine theta. Why? Because for the y direction we have v minus u sine theta, and this is for single wave. And now what is the work done per second? The force into velocity is your work done, and if you take the kinetic energy of the jet, it is like half m v square. Here you can see m is rho a v. Why? Because the kinetic energy of the jet you're taking before the striking the plate, not after striking the plate. If you're taking the mass after striking the plate, then what you're going to get here is rho a v minus u, but here now you're going to get rho a v. Why? Because kinetic energy of the jet before striking the plate. And now v square you took here, and finally what you're going to get is half rho a v cube, and the efficiency is nothing but outlet divided by inlet. What is your outlet? Work done. What is your inlet? Kinetic energy. Oh, by the jet. And we know we already simplified what is work done just right here, and we know what is kinetic energy supplied by the jet, and finally what you're going to get is efficiency. Yes, now we'll see series of lines. Here the series of lines means, for example, see here, first we have the vein, some plate or vein here, or any inclined or flat plate. After striking this, it will move towards some point, okay, and next this will be your 1 and this will be your 2. After some time again it will be like 2, it will be like 3. That means your plates goes on increases like series. This is, this will be 1, this will be 0. Clear? That means after striking one plate again you will get another plate to the sessions. Okay, and now the mass of fluid striking the veins per second is rho AV. So that's what, if it is a single vein, then your mass will be rho A V minus U. But here it is like series of veins. What happens is, instead of relative velocity, you are taking only the velocity. So that's why you are getting rho AV. And now the thrust or the force exerted by the jet on the vein, the force in x direction is equals to rho AV, which is mass per second, and this is V minus U, with which the jet striking the plate, and this will be your final velocity or exit velocity. You're going to get the velocity over here, which is like V, but in the x direction, what you're going to get is V minus U cos theta. Clear? Sorry, here it is like V minus U. Clear? This is your exit velocity, and exit velocity in the x direction. Clear? And finally, if you simplify this, what you're going to get is fx, that equals to rho AV V minus U into 1 plus cos theta. And now the work done per second, which is fx into U. And you know what is fx, and if you substitute this U, what you're going to get is, well, work done per second. And the kinetic energy, you know, which is like half mv square. And what is m? Rho AV. And this is your kinetic energy supplied by the jet. And this is the efficiency, which is like outlet divided by inlet. The outlet will be the work done on the wheel, and the inlet will be the kinetic energy supplied by the jet. And finally your efficiency equals to 2u v minus u 1 plus cos theta divided by v square. And this is the second case in the curved plates. Okay, second case in the curved plates. Here the jet will strike the plate at the one tip or tangentially at the tip. Clear? You can see here, this is your tip, this is your curved vein, this is your curved vein, and this is your tip. At this, on this tip, your jet is striking with velocity v1. Okay, we'll see clearly. See here, this is your nozzle. This nozzle is making some angle which is like alpha with respect to the horizontal, and this alpha we call blade angle. Okay, and with what velocity it is striking the vein at the tip is v1. After striking the vein at the tip with the velocity v1, this particular vein will move horizontally with the velocity u. Horizontally with velocity u. You can see u. So it is an inlet one, so that's why we are designating with v1 and the u1. And for these two, we have a velocity which we call a relative velocity, and by that you can draw a line here which is like vr1, and this relative velocity is making some angle with respect to the horizontal, and that angle is theta, we call it as blade angle. Okay, here the alpha is jet angle and theta is the blade angle. Okay. And now here the VW1, which is the frill velocity, and this one is your flow velocity. So this one is your frill velocity, and this is your flow velocity of the inlets. And moreover, we can call these are horizontal component of your V1 and the vertical component of your V1. Okay, flow velocity, which is like flow velocity will be your vertical component of V1, and VW1 is a horizontal component of the V1. And similarly, you can see the angle here, and this is the angle making by the relative velocity in the direction of motion of wing. In the direction of motion of wing, and these two are alternate angles, which is like theta. And now these are the outlet velocity triangles, and this is your outlet tip. And now what you're going to get is here the relative velocity VR1, so VR2, and this is your phi, that is the angle by which the relative velocity is making with the horizontal component, and that is your blade outlet blade velocity, and this u2 is the blade velocity in x direction. And now if you simplify these u2 and the vr2, you're going to get this v2, which is the absolute velocity of the outlet. And now this absolute velocity is making some angle with respect to the horizontal, which is like beta, and we call this as jet velocity outlet jet velocity. And now here we have three cases with respect to this beta, and if this beta is more than 90 degrees, it will place here. If it is equals to 90 degrees, you are going to get the v2 here. Okay, and now if beta is less than 90 degrees, then you are going to get the triangle like this. Now here the beta value is less than 90 degrees. Clear? VW2, which is the frill velocity, will becomes 0 if the beta is 90 degrees. If beta is 90 degrees, then your v will velocity, which is like VW2, equals to 0, and the mass of water striking the plate is equals to rho a vr1, which is the relative velocity I have to consider here, and the force exerted equals to fx, which is equals to rho a vr1, and this is the mass per second. And now vr1 cos theta is your inlet velocity in x direction, and minus vr2 cos pi is the outlet velocity in the x direction. And if you simplify this with respect to the equations here, okay, what you're going to get is fx rho a vr1 is equals into vw1 plus vw2. Okay, and already we discussed about this theta, which is like when beta is acute angle which is less than 90 degrees, then this will be the your equation. And if it is beta 90 degrees, then your will velocity will be 0. If the beta is obtuse, that means if it is like greater than 90 degrees, then this is your equation. But we have a general equation which is rho a vr1 into vw1 plus or minus. You have to consider this plus or minus. Why? Because if the beta is less than 90 degrees, then you have to take plus. If it is greater than 90, then you have to take minus. Okay, and now the work done per second by the jet of wing is equals to force into velocity. If you consider this work done per second per unit weight of fluid striking, then this will be your the work done per second, and this will be your weight of the fluid. And now work done per second will be this one, and this is your weight of the fluid, which is like mass into gravity, okay, which is like W equals to mg. And finally what you're going to get is 1 by g into vw, wheel velocity plus or minus wheel velocity of outlet into velocity, blade velocity. Now we'll see the series of radial vents, and this is the last case of this session. And now we have the veins here, which is like series of veins, curved veins, okay. And from the midpoint of your total wheel, see, this wheel will be like a circular. To this circular wheel we have the blades, okay. And the tip have the radius of inlet tip have the radius of r1, the outlet tip have the radius of r2 from the center of your wheel. We'll see clearly this one. This is your center of the wheel, and this is outlet of your tip, and this is your inlet of the tip. And now this is a similar case what we discussed up to now, like inlet triangles, and these are the outlet triangles of your radial series of radial vents. But the thing is, you have to consider the angular speed here, okay. Angular speed, which is like w, and r1 r2 are the radii of the wheels, and u1 is equals to uh, angular velocity into radius, u2 equals to outlet velocity of the blade, which is like angular velocity into radius, and mass of the water striking per second, which is like rho a v1, clear. And now for series of vines we have to consider, for the series of vines we have to consider v1, okay. If it is a single vine, then you have to consider vr1. You know the reason why, right? A movement of water striking the veins per second is equals to rho a v1 into, this is mass into velocity is your movement, mass into velocity is your movement, clear. Similarly the movement of water per second at outlet, and this is your negative case, which is getting at the outlet of your vein. And finally the angular momentum per second at the inlet, which is nothing but momentum into radius, and this is the momentum for the rho a v1 is the momentum, this is the rho a v1 vw1 into r1, and the angular momentum per second at outlet, this is angular momentum per second at outlet, which is like mass into velocity into radius. And finally the torque exerted by the water on a wheel is T, which is equals to rate of change of angular momentum, and rate of change of angular momentum is nothing but initial angular momentum per second minus final angular momentum per second. And we know what is initial angular momentum and the final angular momentum. After simplifying this, what you're going to get equals to torque is equals to rho a v1 into vw1, which is wheel velocity into radius of inlet plus wheel velocity outlet into radius of outlet. And what is the work done? Work done per second on a wheel is equals to torque into angular velocity. We know what the torque is from the previous case, and this is your angular velocity. If you substitute this, what you're going to get is work done per second on the wheel. And these are the three cases when we have three different beta values. What is beta? Angle, blade angle. If it is greater than 90, less than 90, and equals to 90, we have three different cases. And from these three different cases, which is like the general expression for work done per second is rho a v1 into wheel velocity u1 plus or minus wheel velocity u2, and this is the efficiency, which is like outlet divided by inlet. What is the outlet? Work done per second, and this is the inlet, which is the kinetic energy per second. If you substitute these two values, you're going to get the efficiency of the vane, which is equals to 2 into wheel velocity into blade velocity at the tip inlet plus or minus wheel velocity and the blade velocity at the outlet divided by v1 square, which is inlet velocity square. Thank you.